Welcome back, ladies and gentlemen. In this video, we're talking about Newton's universal law of gravitation. And this is coming on the heels of looking at Kepler's laws of orbital motion. And so we want to kind of recall what Kepler was saying. That if we have finger out of the way. Sorry. You have a planet orbiting the sun, let's just say. There is a radius to that orbit, and even if it's not a true circle, if you consider an ellipse, then there would be an average radius, even though it changes, so there's an average. But what Kepler was saying, his descriptions of orbital motion focus on how a planet's distance from the sun affects orbital speed and orbital period. So how the radius is going to affect the orbital speed and the orbital period, capital T, right? Well, that's what Kepler focused on with his laws of orbital motion. What Newton focused on instead with the law of gravitation is force and acceleration. Recall that what we've learned about Newton's second law of motion, and really it started out just F equals ma. Okay, and this really is net force. Well, using Newton's second law to find the weight of an object, the force of gravity acting on an object, we simply said that force of gravity is equal to the mass of the object times gravitational acceleration, or you could say the acceleration due to gravity. But Newton actually didn't write it this way, at least not at first. We're going to see later on why g is 9.8, but we're not going to get into that right now. Newton realized that for a larger planet, let's look back at this diagram. If you had a larger planet orbiting the sun, then it would take a larger force to produce the centripetal acceleration. Remember that, centripetal acceleration toward the center of the circle. It's going to take a larger force if the planet has more mass. And so as the mass increases, the force does, just like it does here. But what Newton also realized was that if the planet was orbiting further away, if the distance away from the sun was greater, so for a planet over here, where radius is larger, then the force would be weaker because of that increased distance. So the force would be weaker, force would be smaller, further away from the source. So what Newton ended up coming up with is this law, this description for gravity as a force. And this description is in the form of an equation. And so here we go. Force of gravity is equal to g times the mass of object 1 times the mass of object 2 divided by the radius between the two objects squared. That is, right there, Newton's law of gravitation. So we're going to break that down and look at all the important business that's going on here. This relates the gravitational force between any two objects, objects M1 and M2, or object 1 and 2, and they have masses, right? And what this is saying is that this force depends on the two masses, M1 and M2. So if the masses are larger, the force is larger. If the masses are smaller, the force is smaller. But the force is also inversely proportional to the square of the radius. So there's a proportionality, there's a relationship here. So we can say force of gravity is proportional to the inverse of the square of the radius. You'll hear this called what's known as an inverse square relationship. where one thing is related to the inverse of the square of another thing. And that is what's going on here. As the radius increases, well, the force of gravity does get weaker, but so there's your inverse relationship, but it's inverse squared. So
people at the door, I'm assuming it's the TV guy.
So next let's look at how this equation works. So Newton realized that any two objects are going to attract each other with a force. And the force is gravity. And the force of attraction is going to happen along a line, an imaginary line that is just linking the two objects. So there's a force this way on that one and a force this way on that one. And so really it's the same force, same amount, acting on different objects in opposite directions. So you kind of see action or reaction. This is the third law of motion happening here, but just get the idea that both of these are affected and there is a distance between them. The distance is the orbital radius if we're talking about the orbit of a planet. This could be M1 and M2. And it could be anything. It could be the sun and a planet orbiting the sun. We can imagine an orbit. This could be the Earth, and it could be the moon orbiting the Earth. This could be the Earth and a satellite in orbit around our planet. Well, anything really. So here's getting back to the equation and how this works. Masses M1 and M2 are attracting each other gravitationally, and we can figure out how much force there would be. So let's say what we have is, I'm going to look at a slightly different example, not something orbiting something else, although it works for that, and you'll see that. I want to see how much force of gravity there is between an apple and the Earth. So imagine the Earth, and this is going to be a bit of a silly diagram. Here's Earth, and we have an apple sitting on the ground. Definitely not drawn to scale here. Let's see. Apple sitting on the Earth. And so we need to know a couple things in order to make this equation work. First of all, where is the apple? So we actually look at this distance r as a radius of an orbit most of the time, right? But it's truly measured to the center of each object. Well, the center of the apple is real close to the ground. How far away is the ground from the center of the Earth? Well, that would be Earth's radius. So, radius of Earth is typically how you'll see this written. And so, the radius of Earth. What is that value? It turns out it is right around 6,380 kilometers. But I'm not going to want this number in kilometers. I'm going to want it in meters. So there's 1,000 meters in each one of these. So I'll just add 3 zeros to that number. 6,380,000 meters is Earth's radius in meters. Here in America, we put commas every third digit. If you're European in nature, then you just leave spaces. Never mind that. So we also are going to need a couple masses. We need the mass of the Earth and we need the mass of the apple. Remember, M1 and M2, those are masses. Well, we have mass of an apple. And I don't know, a good large apple might be 250 grams. But I don't want this measurement in grams, I want kilograms. So this is going to be 0.250 kilograms. This marker is on his way out. Sorry about this. All right, and we need the mass of Earth. And this one is a number that you can look up in your textbook or online. You know, the source is going to be unimportant. And you see that you get 5.97 times 10 to the 24 kilograms. Okay, this is a number. This is one number, not two numbers. This is one number written in scientific notation. And if you're not familiar with scientific notation, come and talk to me. It's a skill I can help you with. Once you see it, it's very easy to deal with. But you need to think of this whole thing as one number, not two. Okay? It's a big number, by the way. What this essentially means, of course, is you look at that decimal point, and you're going to move it 24 spaces to the right. So you move it this way, 24 spaces. You have to add a whole bunch of zeros and make that number really huge. Okay, fine. But now, what is going to be the force of gravitational attraction between these two objects? So looking back at this equation, force of gravity is G times M1 times M2 divided by R squared. But we need this. What the heck is this capital G business, right? We'll get to this solving this problem in just a second. Let me put it right here for us. It's capital G. G is what's called the gravitational constant. That's its name. And it is just a number. It has units with it, but it's a number that makes this equation work, and it makes it work anywhere in the universe. That's why sometimes this is called the universal law of gravitation. And G has a value that will always be the same anywhere in the universe. 6.67 times 10 to the negative 11 is the value. And the units here will look a little odd, a little complicated. It's Newton times meter squared divided by kilograms squared. So that is G. And so we have to use this value in this equation whenever we have to do this. And it doesn't matter if you're talking about two planets, if you're talking about a planet and a moon, a planet and a satellite, a sun and a planet, it doesn't matter. You could be talking about two basketballs. G is still this value. 6.67 times 10 to the negative 11 power. Well, the negative sign here means you move the decimal point to the left 11 spaces, making this a very small number. So let's get back to our problem about the apple on Earth's surface. What is the force of attraction that's occurring here? So the last thing we have is this value for G, right? 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. So we can set up the equation. You know what? I'm going to start this on a new sheet of paper, so I've got more room here. So the force of gravity, and this force, of course, is going to be affecting both the apple and the Earth. Forces really always occur in pairs. Another way to think of this is really a force. There's only one force, but it affects two different things in different ways. So G, I'm going to write the G first. 6.67 times 10 to the negative 11. I'll include all the units the first time, but generally you can stop writing these. Meter squared per kilogram squared. Okay, there's G. And now I need M1. And I said that, well, it really doesn't matter which is which. The way I've drawn it here, M1 would be the Earth. So I need the Earth's mass, this number. So I have M1, 5.97 times 10 to the 24. Come on, give me a 2, 4. Sorry about that. And this is kilograms. And then M2 will be the mass of the apple, which I said was 0.250 kilograms. Extend that line. and I need to divide by the radius squared. So the radius, the distance between the centers of these two objects. So from the apple to the center of the Earth. Well, that's just going to be Earth's radius. So there we go, 6,380,000 meters. 6,380,000 meters. But that is squared. Okay, so this happens from time to time. You have an exponent in an equation, and sometimes the exponent accidentally gets left off when you're solving an equation. Watch that. Be careful of that, so don't lose track of that guy. And when you crunch all these numbers, it isn't so hard to do on your calculator. You end up getting 2.45 newtons. There's our answer. That is the force of gravity acting on the apple. It's also the force of gravity acting on Earth that's caused by the apple. Remember, it's a relationship. You got both things happening at the same time. All right. So, okay, good. That's interesting. We can use the equation. That is how it works. There's something interesting I'd like to look at, though. So, for comparison. What if we had found the force of gravity acting on the apple by using this much simpler equation? Then what would we find? Well, the mass of the apple, 0.250 kilograms. And the value of g, well, we know that, 9.8 meters per second squared. And you do this math, complete, and you get 2.45 newtons. It's the same. What the heck, man? Well, okay. So here's the deal. Why use this much more complicated equation when it sure seems like this much simpler equation gets you the same answer, right? Why bother with this one? Well, the answer is quite simple. This one only applies to something at or very near Earth's surface. This thing right here. G is 9.8 meters per second squared at or near Earth's surface. And if you go anywhere else, it changes values. If you go further away from the surface, if you go to a different planet, it's different. So this cannot be thought of as a universal type of equation. You can't use this everywhere. It's limited. But this one, you get to use this anywhere you want. As long as you know two masses, you know the distance between the masses, then you can find the force of gravity between those two objects. You're good to go. All right. So let's look at an example. Why use the more complicated equation? What if you wanted to find the force of attraction between the Earth and the Moon? Let's look at that. So the example with the apple on Earth's surface was a little, I don't know, it was interesting, but maybe a little simple. Let's get something bigger here. If we have Earth in the center, there's the Moon orbiting Earth. All right, now not drawn to scale, obviously, but there is a radius, a distance between them, and we have some masses. So looking at this problem, mass of the Earth, again, 5.97 times 10 to the 24 kilograms. We need the mass of the Moon, and the mass of the Moon turns out is 7.35 times 10 to the 22 kilograms. And we will need this value of r in between them. So the orbital radius of the moon around the Earth is going to be 3.85. These are things you can look up. I do not expect you to memorize this. 3.85 times 10 to the 8 meters. If you were to look up this orbital radius of the moon, and it gave you the number in kilometers, you just convert. It's no big deal. So with these values, I can find the force of gravity between the Earth and the moon. Here's the equation. M1 will be Earth. M2 will be the moon. I think this marker's just about done, isn't it? All right. Let's switch colors here. And so I have my gravitational constant, 6.67 times 10 to the negative 11. I'll do this one more time for you. Newton meter squared per kilogram squared. Okay, there's G. Now I've got mass of the Earth, 5.97 times 10 to the 24 kilogram. I've got mass of the moon, 7.35 times 10 to the 22. Kilogram. Extend that line. And the radius, the orbital radius of the moon, 3.85 times 10 to the 8. This is in meters, and I want that in meters exactly. And that is squared. Again, keep track of your exponents. So, plug in numbers into the calculator. It occurs to me that it might be helpful for you to see this in action. So, handy dandy calculator. And you know that, at least on the iPhone, if you tilt it this way, the whole thing rotates and you get a whole bunch more buttons. I thought that maybe this would show up a little better on the video. If I don't want to get too crazy. Well, okay, you can see it that way now, but that's just not going to be helpful. So here's the deal. As far as using a calculator, I can show this to you in class. It's not a problem. Just remind me that you'd like to see that if that's the case. But when you crunch these numbers, you get this answer of 1.97 times 10 to the 20 newtons. So that's a huge number, guys. So check this out. Imagine that decimal point moving 20 places to the right. There's 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15, 16, 17, 18, 19, 20. Boom. That's a lot of newtons. Commas. We like our commas. Every 3. Holy cow. I don't even know what the name is for this number. That would be millions, billions, trillions, gazillions, something. That's huge. All right. So that's why we like to use scientific notation when appropriate. It makes the number easier to write. And it's not hard to see that this is going to be a very large number based on that exponent. Okay, so again, we see this, the main equation, this guy, in use with another example. In the first example, there was the apple on our surface. Here we have one thing orbiting another, and it works the same way each time. This is where things get interesting. So that's it right there. The law of gravitation. That is it. One equation. It's easy to work with. But there's more. Of course there's more. We can look at the orbits as nearly circular, meaning we have an object moving in a circular pathway, and that means there's a centripetal acceleration, right? So recall that centripetal acceleration is equal to the speed squared divided by the radius of the circle. Well, how could that orbital speed be calculated if this is an orbit? So if we imagine an orbital, a circular orbit, and this is fine to do. So we want to know, for a planet orbiting the sun as an example, what is the velocity right there? And that velocity will be working with the radius to determine a centripetal acceleration. There's a radius here. And the centripetal acceleration is the acceleration toward the center of the circle. And that acceleration is what is changing this velocity, causing that velocity to change direction as time goes on, right? Well, how could we use that to figure, or how could we figure out this orbital speed? How could we figure out that v right there? A velocity, any velocity, is real simply a distance traveled divided by time. I said velocity. Really, we're talking about a speed here. In this case, one easy thing to look at is how far does the planet move in one orbit. So the distance traveled in one orbit sure looks like the circumference of a circle. Capital C for circumference. And this time that it takes to make one complete orbit, well, the time we call the period for one orbit. It's the orbital period, right? But we can look at circumference one more time, because we can say, well, a circumference of a circle is equal to 2 times pi times the radius of the circle. And there we have something. So we're going to make this substitution. We're going to take this and put it into this equation where we see the v. And we're going to rewrite this equation. We're going to say 2 pi times radius divided by the period. This whole thing is squared. Then we're going to divide by the radius. So how does this boil down? Well, 2 squared is 4. Pi squared is pi squared. Radius squared is radius squared. Period squared. And notice it's in the denominator. So I'm going to bring that guy down to the bottom of the fraction. Period squared. And down here I also have a radius. And the interesting thing is this radius will cancel with one of those. So we get rid of that exponent and I'll leave 1r on top. So 4 pi squared r divided by period squared. Okay. So I have this relationship, this sort of a new way of looking at centripetal acceleration. Well, the net force acting on the planet is the mass times the centripetal acceleration. This is just writing Newton's second law for a planet in orbit around the sun. The net force is a force acting toward the center of the circle. You might call that the centripetal force. Cool, but it is also the net force. And so look at this. We're simply going to make a substitution of this business in for centripetal acceleration. And we're going to rewrite this equation and say, well, we have the mass. Now, what mass is this? This happens to be the mass of the planet, right? Mass of the planet times 4 pi squared r divided by the period squared. And that's equal to the net force acting on the planet. But wait a minute, what's causing this net force, right? If we have a planet orbiting the sun, well, this net force pulling the planet toward the sun, that force right there, isn't that the gravitational pull of the sun? Well, of course it is. So net force is really a gravitational force. A gravitational force is this guy, right? Well, of course. So where m1 could be the mass of the sun and m2 could be the mass of the planet, and what we're going to do is set these two equal to each other. I'm going to set that up on the next page. Okay, so it looks like we can do this, and since I have this equal to net force and this equal to net force, I can put those two things equal to each other. And so here's what this looks like. M1 was mass of the sun, M2 was mass of the planet. There we go, so that's one side of the equation. And on the other side of the equation is this business, mass of the planet times 4 pi squared times radius divided by the period squared. Okay, so I'm going to just kind of simplify. I'm going to cancel anything out that I'm allowed to. Right away I see the period, it can cancel. And what I want to do is sort of simplify and get rid of fractions if I can. So how I get rid of fractions is if I have dividing by r squared on this side, to get rid of that, I will multiply both sides by r squared. So multiply this by r squared. And I do the same over here, and that gets rid of r squared here. Well, I'm dividing by period squared on this side, so I'm going to multiply both sides by period squared, and that gets rid of period squared here. And I no longer have fractions, which is kind of cool. And I've also already canceled out the mass of the planet. Turns out that that is not a part of this. So I'm going to show you some simplification, clean this up a little bit. Period squared times g times mass of the sun equals 4 pi squared r times r squared. So let me write this out. 4 pi squared, r times r squared is r cubed. And the way this is usually thought of is trying to isolate t, because maybe not truly isolated. Watch this. I'm gonna divide both sides by g, the gravitational constant, and mass of the sun. So here we've got cancel, 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 cancel. And I'm left with t squared is equal to 4 pi squared r cubed divided by g mass of the sun. And I'm going to do something kind of slick. This isn't math, this is just a different way of looking at this side of the equation. 4 pi squared divided by g mass of the sun. And I'm going to write the r cubed here. And you know why I'm doing that? Check this out. This is really going to bake your noodle. See how I've got period squared there, and I've got r cubed there, and I've got some unknown in between, some multiplier. That should look real familiar. That should actually look just like something you saw in a previous video, right? Where I actually don't have it handy at the moment, where you had period squared is proportional to r cubed. Does that look familiar? That is Kepler's third law. That's one way of looking at Kepler's third law. So using Newton's law of gravitation, we can see more clearly how Kepler's third law works. We now know what goes here in front of the r cubed. And really, it's not even left to look like this. It's sort of, if we take the square root of both sides, we get the period of orbit of any planet or satellite is equal to the square root of this whole thing. Well, I'll show you that. Square root of 4 pi squared r cubed divided by g mass of the sun. And so when you break this down, the square root of 4 is 2, square root of pi squared is pi. You get 2 pi. And you're left with r cubed divided by g divided by mass of the sun, all under the radical. So what we have here, coming out of Newton's out of Newton's law of gravitation, is an equation that shows us the period of a planet. The period of a planet, how long it takes the planet to orbit one time around the sun, seems to depend on how far away the planet is from the sun, that's r, and also depends on the mass of the sun. Now, what if we're not talking about a planet in our solar system? What if we're talking about a planet orbiting a different star? Well, this is an interesting equation because what we can do is say, well, we can pretty easily measure the distance between that planet and the star, and we can pretty easily see how long it takes that planet to make one orbit, so the time, the period here. And if we know those two, well, g is the same everywhere. What that allows us to do is actually calculate the mass of that other star. That's when astronomy gets really interesting. Real applications. That's work that astronomers actually do when they are making these observations, looking through their telescopes. Why are they bothering to look? Well, if you know the mass of a star, then you start to understand how large the star might be, how much energy it's putting out, the stellar evolution, its life cycle, how long will that star live, what sort of stages will it go through. So one more thing about this, but that's what makes that kind of exciting, kind of interesting, is that once you can, through some easy things easy to find, easy to observe, you can observe a period very easily, you can observe a radius pretty easily, you can learn the mass of that star, including our own sun. And once the mass is known, all kinds of other knowledge starts to flow your way. Well, in this equation, I want you to notice how the mass of the planet does not affect its orbital period. You don't see mass of the planet anywhere in here. It canceled out pretty early on. So it doesn't matter how massive the planet is. Its period will only depend on how far away it is from the star and on the mass of that star. So, but this equation also works if it's not a planet orbiting a star. What if it's a satellite orbiting a planet, or a moon orbiting a planet? It still works. The period of orbit of the moon, let's say, can be found, same equation, if we just change one little thing. Same exact relationship, still using g, gravitational constant. But now what we do, if it's the moon orbiting the Earth, right here we have to take the mass of the Earth. That's it. That's the only thing we change, and this equation will allow us to calculate the period of orbit of the moon. But the trick is, this isn't what we normally want to do. The equation is written this way to show how it's the period that depends on those two things. But instead, what would astronomers do? They wouldn't measure the mass of the Earth and then the radius of orbit. to find the period, they'd measure the period. That's an easy thing to do. They'd measure the distance from Earth to the moon. That's relatively easy to do. Measuring the mass of the Earth, that's not easy to do. Holy cow, what would you do? What kind of experiment would you perform to measure the mass of the Earth? It really can't be done, but it can be found. You would rearrange this equation and isolate mass of the Earth. You would measure the radius between the Earth and the moon. You would measure the orbital period of the moon. And you would calculate the mass of our planet. And just like knowing the mass of a star, once you know the mass of a planet, all sorts of other knowledge starts to flow your way. Because with mass and size, you can get density. And with density, you can learn about what the planet is made of. And you can compare that planet to other planets and what they're made of. And planetary formation starts to kick in. You start to learn about the interiors of planets and seismology and earthquakes, continental drift, and plate tectonics. And it's wonderful. Huge amounts of knowledge start to come your way. Concrete knowledge that you really don't doubt. It's valid stuff. It's not guesswork at all if you know the mass. And so from Newton's work, building on Kepler's work, we can get there. It's really cool stuff. Enough here in this video. If you have any questions about the law of gravitation, let me know. Thanks for watching. I'll catch you next time.